Well, welcome everybody. Welcome everybody. The clock is ticking, or in the case of that, oh, it is working now. Before it was thrashing inconsolably. All right, even that clock is advancing, so I'm going to go ahead and introduce myself. I'm Nat Fortune in the Department of Physics, and this is a Sigma Psi Lunch Talk series, but it's also the first in a series of Climate 101 talks being sponsored by the Year on Climate Change. And so I'm really glad to see all of you here. And let's just jump right in. My goal today is not to convince you that I know why the Earth is warming. My goal today is for you to be able to have a conversation with your neighbor and be able to have your neighbor understand why the Earth is warming. So I'm going to give some fairly labored examples, and I'm sure you can come up, in fact, I encourage you to come up with your own, in terms of things that people already understand, that focus on the basic elements and what has to be done to change the warming behavior. All right, so let's start first with the fact that the Earth is indeed warming. And there's much evidence of that. What I'm going to show you is a short 30-second video of how temperatures on land and sea have changed since 1850 or so. And to be able to show you as a result, for comparison, we're going to take 1950 as our reference year. And anything or anywhere on the globe that was colder than the average temperature for the entire globe, the global average temperature in 1950 will be on the blue side, and anything warmer will be on the red. On the bottom of the screen, the global average temperature will be playing as well. All right. So what do we see happen? Well, we can see little things like winter and summer. And we can see they occur in the northern and southern hemisphere at different times of year. And we can see even when there is winter, say in the northern hemisphere, that there are parts that are warmer than usual and parts that are colder. And similarly for the other season as well, that a global average temperature does not mean that it's the same temperature everywhere on the globe. Well, okay, that went fast. And we're going to work out, yeah, let's just go back to that. Let's hide that one at the moment now. I think if I restart there, we'll be okay. All right. So you may have noticed a certain color shift for the average temperature here, where it went from blue to red. And, oh, I wish it would stop doing that. Okay. Let's stop our, okay. This is supposed to be a technological tour de force here that I'm presenting to you. Okay. It probably would be without my intervention. So anyway, the question is why, and that's what we're trying to answer here. And so there are, interestingly, why is the other screen showing up on this one? Well, I think that we will just turn that one off for the moment. Okay. Things that never happened before now get to happen here. So I want to turn the displays controls. I'll just turn that one off if I can. No. That doesn't work either. Was I saying something about a technological tour de force? Okay. This part will get edited out, right? Okay. Okay, and here we'll go for the right one. The right one is just the desktop Zoom screen sharing. Well, I don't know what is going on that one there. Let's try switching to... Okay. All right, let's try that instead. Okay, now I need to change the room lights just a little bit. for here to bring things down and still be able to see what we're doing. So I'll start by dimming to what the projector settings are. And then I'm going to try to bring up some lights. Some main spots. All right, so that you can, well, that's not going to work for that. All right, how is that? Okay, all right. So here's 3 useful analogies to guide our thinking. And the first of them is of overflowing bathtub. Can you see me here with this amount of light? Okay, great. So the analogy here is one that I think you can demonstrate on your own as well. But really the main physics that you need to know to understand why the Earth is warming and why CO2 levels are rising and why they're connected is the fact that if you fill a tub faster than it drains, right, if you're adding water faster than you're removing it, the level in the tub is going to rise. I know this doesn't sound astounding in any way, but it's the basis of what we need to know. And so let's think about that. Normally we fill a tub and then we drain it. And as we're draining it here, I can count how long it takes to fill it. 1001, 1002, 1003, 1004. And when I do that, okay, it took about 4 seconds to fill up to this level on the glass. Now, you are all probably familiar that as the level drops, in fact, the rate at which this tub will drain will decrease. So that now if I'm going to let it go a little bit lower, now when I try 1001, 1002, 1003, 1004, 1005, 1006, and the lower it goes, the lower the rate that it drains. All right. Now you've experienced this in a house as well, in that, the house will cool off quickly at first and then more slowly if you stop heating it there. But what's important for our demonstration here with a system like the Earth, where we're simultaneously heating it from the sun and then re-radiating energy back out to outer space, is that tub, the Earth tub, is draining and filling at the same time. So if we take a tub, whoa, that's too full. If we take this tub, if I fill it faster than it's draining, you see the level rising. If I fill it at the rate it's draining, you see it stays steady. All right, now let's fill it. If I fill it more, it rises to a new steady level. It's draining faster because the level is higher, and I'm filling it faster than before, but now the rate at which I'm filling it once again matches the rate at which it's draining, and so the level stays the same. The analogy here is that this could be the temperature of the Earth and the rate at which we're heating it and removing it. I'll illustrate a little further later, but this is maybe not a very disturbing thing unless you have to clean up afterwards. I mean, just get some towels, clean up. What's the problem, really, for this? So for those of you who would like a more disturbing analogy, after the, and it's gone away again. Isn't that interesting? Okay. I've tried to point out steady state equilibrium is not where nothing happens, but where the rate in is matching the rate out. Okay. It could be volume of water in, volume of water out. It could be rate of energy transfer and rate of energy out. What determines whether the level rises or falls is not whether I'm filling faster or slower, but whether I'm filling faster than it's draining. If I'm filling fast and I ease up, it will still rise. I mean, it could drop if it drains faster. I could fill up and ease up and it still rise if it's still filling faster than it's draining. Okay, so you have to think about two things, the input and the output. This also works for student debt, but that's a different discussion. So here's my more disturbing analogy. You could think of it, well, one reason it's disturbing is the artwork. But some not very artful sailors are trying to bail out a leaky boat, which is taking on water and approaching a tipping point. Now, if their sailors are able to bail out the water at the rate it's filling in, so if they have a situation where the rate at which water is coming in matches the rate at which they bail it out, then they may have their feet wet, but they won't sink. If, however, they're bailing as fast as they can and are taking on water at an ever-increasing rate, the sailors better be able to swim. Okay. One other, again, it matters not whether water is coming in or not, but how it's coming in compared to bailing it out. Let's take our next one. All right, and I figured this out. A passive solar heated house. Okay. Here, the house is warming because sunlight is coming through the windows, warming up, say, some concrete blocks on the floor. They're re-radiating energy. And at the same time, heat is flowing out the walls and ceiling of the house. And so you have a rate of heat gain and a rate of heat loss. The energy transfer in has to match the rate of energy transfer out. And if we take as a measure a change in temperature between the inside and out, a difference in temperature, then the rate at which the rate of cooling, rather the energy out, is going to be proportional to that difference in temperature. And you know that, right? You know that because if you try to keep the temperature at, say, 30 degrees Celsius, and it's 10 degrees C outside, you're going to need to supply fuel, burn the furnace, or have the sun shine twice as the rate, because you're going to, then if it's 20 degrees and 10, because if you try to maintain a 20 degree difference between inside and out compared to a 10 degree difference, you lose energy at twice the rate. Double the temperature difference, double the rate. When the temperature goes inside to out, there's no heat loss at all. So whether the house will warm or cool will depend on the rate at which the sun is shining or a furnace is burning compared to the rate at which it goes. That rate will depend on the temperature difference you're trying to maintain. And this is somewhat of an analogy to our Earth, because we are a passively solar heated planet. All right, and so the question is, what controls the rate in? What controls the rate out for our little overheated Earth? And what you can see in this situation here is that we have visible light coming in and infrared light coming out. Now let me get a pointer here for this to help you with that. Okay. Visible light, it's sort of visible, in, and some of it is absorbed and some is reflected by the ice that remains on our planet. Okay, if we were to eliminate the ice, if the ice goes away, then the reflection decreases and the amount absorbed increases. All right, and then so that the rate in for the energy transfer from sunlight will rise. Okay. Now, what controls the rate out? Well, we know that there must be some energy loss because we know that the Earth hasn't melted, even though it's been warmed by the sun for a really long time. And it is actually re-radiating out energy. It's radiating it out, as I'll try to demonstrate, in the infrared. That if the infrared radiates back out to space, there should be some balanced temperature at which those rates match. If we were to capture some of the infrared leaving the Earth and coming back, that would decrease the rate out. So things that control the rate in are things that affect how much of the sunlight is absorbed versus reflected. Things that control the rate out are how much of the outgoing energy in the form of infrared light is being captured and returned. So you see in this picture you have infrared light going out and infrared coming back in. But let's try to convince you about what's going on with the infrared. Again, if the rate going in doesn't match the rate going out, the temperature will change because of the amount of energy. Infrared electromagnetic radiation, infrared light, is really just another form of light. Electromagnetic radiation happens at all wavelengths and frequencies, and there's a small band of it which is our visible light window that our eyes are able to see. And that one is here. But beyond, on one side of it, at lower wavelength, where each photon of light carries more energy, we have ultraviolet and X-rays. Those carry enough energy to ionize molecules and to cause skin damage. Right? On the other side, you have infrared. Those are longer wavelength, lower energy, and so they can warm you, but they can't cause ionizing molecular damage. So those molecules, yeah, so that's the spectrum that we're dealing with. Light is emitted at all of these. We may not be able to see it. If you ever saw a really bad movie with Arnold Schwarzenegger called Predator, the predator could see in the infrared, right? And so, much like snakes can see mice, tasty morsels at night, because mice emit infrared. In fact, all of you emit infrared. All right. So, in the case of the sun emits in the ultraviolet, in the visible, and in the infrared. And much of the energy, the peak of the energy, is in the visible spectrum. Okay, so I see that sometimes this shows everything and sometimes it doesn't. Okay, here we go. Where the light occurs and where the peak in that is depends on the temperature. At around 5,000 degrees, you're peaked in the visible. As you move down to 3,000 degrees Kelvin, you're peaked in the infrared. And by the time you get, say, to the temperature of the Earth, because anything more than absolute zero emits radiation, emits energy, radiates electromagnetic energy, you're in the infrared, and there's no visible light that we can perceive emitted at all. The other important, this was one of the first triumphs of quantum mechanics, to be able to account for this spectrum and this variation in intensity of the light shown on the vertical axis versus wavelength shown on the horizontal. That why does it peak and then decline at lower wavelength after initially rising? And if you integrate all of the area under this curve of intensity per area versus per wavelength versus wavelength, you get the total rate at which energy is being emitted by an object at that temperature from its surface. That rate is called power. It's proportional to the fourth power of the temperature. So double the temperature of an object, it radiates energy at 2 to the 4, 16 times larger than before. Now, here's the part that gives me hope. You are all literally brilliant. You are, in fact, radiant. And I want to give you a little demonstration of that through the infrared. Okay, so now what we're going to do is we're going to switch over this spectra here to this one there. If I can bring that back, and let's make this one be the HDMI on the left projector. No signal. Why is that? Okay. There should be one. And there we go. So there you are. Now, what's really happening here? Well, first, yeah, there you are. Okay. Notice there seems to be a temperature assigned to you as well. I'm going to change what you look like arbitrarily. All right. What is this doing? This is a camera that can see, like the predator and snakes, in the infrared. And we're looking at one particular wavelength in the infrared. And we're looking at the intensity of the light coming from you here. Now, often we think of the infrared like a heat light, like it's warmth or something. It's light. If it weren't light, we couldn't focus it. You wouldn't have an image. But it doesn't have exactly the same properties as visible light. For one thing, I mean, different parts of you are emitting light at different intensities here. But for another thing, it's sensitive to temperature. Remember that we said that the power was proportional to the temperature to the fourth power. And notice that the intensity at any particular wavelength, say like 2 micrometers here, is going up as the temperature goes up. So this device is saying, hey, I see more light coming off, that part must be warmer. And so from it, it assigns a temperature. And so you can see that this person's nose is about 85 Fahrenheit, and the head is 93, nice healthy head. All right, nobody's running a fever here at the moment. And these glasses, these are the coolest glasses we have seen in this room. Okay, so what I want to point out there, though, is because of that, then, the intensity of light is a measure of temperature. You can just barely make out 3 glasses of water in this room. You can just barely make them out because they're the same temperature as the room. And so they're giving off the same intensity of light, and so they get mapped on, say, to the same color. If I replace one of these with nice cool ice water, or something that was cool ice water at 8 o'clock, when none of these problems happened, I would mention. There we go. This is still 50 degrees because a thermos is a wonderful thing. Whereas this is closer to the room temperature, 70 degrees Fahrenheit. And if I were to take a nice thing of hot water instead into my other container, it's brilliant, right? It can sense the intensity of the light here. And for that reason, we can use a computer to map it onto artificial colors where we have red indicating more intense light and blue indicating cooler, and this color in the middle indicating invisible. All right, so we must not be sensing visible light because they all look the same in visible light. All right. The other thing that helps distinguish infrared light from visible is that you can never hide yourself by hiding behind a window in the visible. But you can make everything disappear with glass in the infrared, because infrared light is not transparent through ordinary silica glass. Right? Instead, it reflects. So, you are giving off light, and if we look at one of you in the audience again with the cool glasses, all right. Notice where you have less insulation. You know, where we have cheeks, we still have a little of that insulation we used to call baby fat. And the temperature inside our body is the same, but the temperature on the outside is now less because it's more insulated. The rate of heat loss is smaller there. But around your skin and your nose, like it's certainly in your forehead, there's very little insulation. Why are the glasses cool? Would you please remove your glasses so everybody else but you can see that in fact, there's a lot of infrared light coming from those eyes, right? It's a really good way to measure the temperature. The glasses look cool. Please go ahead, back again. Thank you. Applause for our audience member. Okay. Because the light is being reflected back, and the computer interprets that as lower intensity, and turns lower intensity as a lower temperature. All right. So everybody here is radiating energy, as is the surface of the Earth. And it's radiating it primarily in the infrared. So how does that help us here understand what's going on? The first is, what does all this have to do with the solar spectra? And the answer is, it doesn't want to tell you. All right, this is a less than impressive, isn't it? All right, I'm not so impressed with the Zoom setup here anymore. But let's try to, I can draw it myself. That's okay. What it all has to do with CO2 is that, see, I threatened to write over it, and then it shows up. Okay. And so sunlight coming in, there's a certain rate at which energy is being delivered. Infrared light going out, there's a rate at which energy is being carried back out to outer space. If there's no CO2, there's a steady state at a certain temperature. There's a quantum mechanical expression for how power depends, the total rate of energy depends on the temperature of the body. And if the sun, the rate at which we're absorbing energy from the sun matches the rate at which we're emitting it from the surface, that will tell you the temperature of the Earth. What happens when you add CO2? When you add CO2, the strangest thing. Okay. When you add CO2, you are capturing some of the infrared that would otherwise radiate out to space, and it's being absorbed by carbon dioxide molecules. Quantum mechanics also tells you that things emit and absorb at particular wavelengths of light, and CO2 is perfectly positioned to absorb large wavelengths of a wide span in the infrared. And so that would mean that some of the energy that otherwise would be emitted is now captured and poured back into the container. That means we are increasing the rate at which we're filling the vessel and decreasing the rate at which we're draining. The level in the vessel must rise. If this is the thermal energy of the Earth and the height is the temperature of the Earth must rise. with the addition of CO2. And so here's how you could map that. The sun, let's assume it's shining constantly at a certain rate, and yet the rate at which you have energy go out is proportional to the temperature of the fourth power. There's some point at which they match, and that point is the surface temperature, is the temperature of the Earth. What happens if the ice melts? More of the sunlight is absorbed rather than reflected, and now you're up here. And so the temperature is an imbalance. You're warming, you're adding faster than you're draining, and so the temperature rises until now you're here at a new temperature that's warmer than before, with power versus temperature on this graph. What happens if you add CO2? Well, one of the effects is to decrease the rate at which you're draining. So at any temperature, you're radiating less power, energy at a lower rate out to space. And so now the curve is shifted this way, right? And so the temperature, again, is warming. The two effects combined, because the warming temperature melts the ice, means that the temperature goes up even higher to here. All right. Well, CO2 levels are rising. This says around 315 parts per million in 1960, around the time I was born. 340 in 1980 when I was in college. It was 360 parts per million when I joined Smith College. And it's over 410 now that I'm speaking to you in this room. Why are they rising? And this is the very last point. It also brings us once back to the third reason we need to know about bathtubs. Why are they rising can be understood by looking at the carbon cycle. There are all kinds of sources of CO2 emission into the atmosphere. They come from everything from plants respirating, animals dying, deforestation, fire. What a sad little upside down animal there. Okay. But, you know, that's death. Your carbon returns to the atmosphere. At the same point, and of course there's carbon coming from the ocean. At the same point, carbon is being sequestered through the growth of a plant, through photosynthesis, and through absorption in the ocean. Those are all natural processes. In addition, we are adding carbon through the burning of fossil fuels. Now, let's see if we can get all the way back to here again or not. You know, I think I will, can we make that come back up? Can we? Yes. And can we call up Calica here and preview there? Okay. Here's that same graphic. And let's just add all these things up. Fossil fuel emissions, respiration, decay, deforestation, ocean inflow, all those emissions together are 198 gigatons a year of carbon. Our total emissions are 10 more than that because we're adding 10 gigatons a year from fossil fuels. The fossil fuels are only 5% of total emissions. So what's the problem, right? Why is the carbon we emit bad and all the carbon from the dead animals good? Seems like, how could we be the source of the problem? You already know the answer. It isn't what you add, but how what you add compares to what you're removing. If we look at the outflows from photosynthesis, from the ocean, from runoff, national sequestration, The Earth removes about 204 gigatons a year. So let's look at the world with us and without us. Without us, emissions minus sequestration, we would actually pull 6 gigatons of carbon a year out of the atmosphere. Without us, there could be another ice age. With us, that 10 gigatons per year changes -6 to +4. With us, instead of another ice age, we can have an age without ice. Why are they rising instead of falling? Because we have changed the Earth from being steady state or even slightly declining over time to rising. We are filling the atmosphere with carbon faster than it can be removed. And in fact, if you look at this, these numbers are only good to one figure. About 50% of what we add is staying in the atmosphere. What's the analogy here? We are filling the atmosphere with carbon at twice the rate it is draining it. As long as we continue to do that, the thermal energy of the Earth will rise and the temperature must rise, right? Even if we level off emissions at the rate they are now, we're still filling it twice as faster as we're draining it. CO2 must rise, temperatures must rise. We go back to the analogy of the sailors. The sailors are busy bailing as fast as they can. And yet the boat is taking on more water than they can bail out. What should the sailors do? Patch the holes, right? Not a bigger bucket, not more sailors, patch the holes. Do you know what you want to do if you want to stop the Earth from rising temperature further? Patch the holes, right? Unless you reduce the rate at which you're producing emissions so that it matches the rate of sequestration, you cannot level off carbon dioxide atmospheres levels in the atmosphere. So there's my answer. Patch the holes. Okay, so let's have a little summary. The Earth, the summary doesn't want to show. There we go. The Earth is absorbing energy at a rate faster than it's emitting energy. As a result, the Earth is warming. That must be the case. See, it's absorbing at a higher rate because we keep adding more CO2. It could rise to a new equilibrium level, but we have decided that rather than do that, we'll add at an ever-increasing rate every year. Right? Instead of patching the holes, we're knocking new holes in the side of the ship. And the captain is encouraging it. That's my only political reference for the whole day. Okay. If CO2 emissions continue to exceed the sequestration rate, atmospheric levels have to rise, and the Earth has to continue to warm. That's why the Earth is warming. Thank you for being here for the talk. I'll take questions at this point, depending on how much time we have for them. No. I think we have room for one or two. Go ahead. I'm sorry, I didn't hear the question at all. That's right. The goal is to be carbon neutral by 2030. Okay. Another question?
Are there any thoughts of manipulating the inputs?
The inputs as well as the outputs? Yeah, it's often what you hear as geoengineering. Like this idea is that, well, what if we were to dim the sun? What if we were to put aerosols up, something in the air that would reduce the amount of light that reached the Earth? That would lower the input. That should plausibly lower the, make it easier for the rate in to match the rate out. But it also would reduce the amount of sunlight coming to the Earth. That would reduce the amount of food that can grow. I sometimes, it's a measure that is born of desperation. And if we become desperate, we will do something that's stupid. Yeah.
What are your thoughts about massive reforestation?
Reforestation helps, right? If you look at what go back to the carbon cycle here, deforestation is contributing 1/10 of what we're contributing. If we stop deforesting, that would be 1 gigaton a year not going into there, right? And we're putting in roughly 5 more than we want. That's about 20% of the problem. If you reforest, and let's imagine that you do it at a rate so you're now having twice as many trees as before, that's another 20%. So it could make a difference in that regard, but it takes a tree 100 years to grow, and it takes a season for it to burn. So it is a measure for the long term, right? And it makes everything else easier. But it isn't enough for us to continue to consume and burn more than the Earth can reabsorb, right? It helps, but we have a problem still. It's not the complete solution. But so when you read like the massive reforestation, that's why they say it could be 20 to 40% of a solution.
Is it clear what the number one fossil fuel generators are?
Well, the great thing about fossil fuels and tracking them,
Down at 10?
yes, in different sectors, there are different types of fuel, right? Because oil is used in transportation and not really in the generation of electricity. Whereas coal and natural gas are used in the generation of electricity and very little, essentially nothing in transportation. The other thing is that we can keep really good track of fossil fuels because we pay money for them. And so we really know the rate at which we're buying and burning them and that. Finally, you can even isolate whether a certain carbon dioxide molecule might come from here or there, and that there are different, all carbon dioxide behaves the same in terms of the infrared properties. But there are different isotopes of carbon. Some of them decay faster than others. If you're burning old carbon as opposed to new, the isotope ratio is different. So there's some tracing that way. If we were to call up this end here, I had a graph I could show you if I have I don't think I have that one there. But another way to do it is to sort of model what emissions are from country location rather than just from industry. This is the path we're headed on. The yellow is the Paris Climate Accords. The Paris Climate Accords do not limit temperature to 2 degrees. They limit to 2 degrees in 2050. They don't limit it because the emissions do not level off, right? And emissions would actually have to decline for that to happen. So let's be imaginative. Let's imagine that we start emissions there and we reduce them 10%. If you want to level off temperature, you have to decrease emissions because we're filling twice as fast as we're draining. I feel like I went away from your question a bit.
That's fine.
Okay.
I was looking for ultimately more on the specifics of who's polluting the most,
Yeah.
both in country and in industry.
Well, this will have to be the last question that we do. Let's see if we can enlarge that. Okay. What you see here is energy use in the US. Similar models are for every country of the world and the world as a whole. And the size of these boxes are showing the size of energy consumption from sources: solar, nuclear, hydro, wind, geothermal, natural gas, coal, biomass, and petroleum. And then it shows where they're going. All of these are going into electricity generation. This one is going into transportation. All right. And can we make that larger? And so you can see according to industry where the energy sources are and which ones are the largest. All of these with electricity generation can become carbon free because we have ways of generating electricity that don't require the burning of carbon. Petroleum, which is, say, 34 out of 100, about 34% of the energy usage in the United States, is 98% oil. And unless you electrify the transportation system, you cannot make that carbon free. Okay, let's quit there. Thank you very much. Patch the holes.